Welcome to solverfy.
All right, so problem number 46 is actually it's one of the cool little quirks of relativistic physics. So it talks about we get the lifetimes that are listed in table 2. They're proper time. So they're measured with reference to the particle itself. So if you are the particle, this is how long you live. But these are such high energies, you have to treat them relativistically. So when you switch to the lab reference, you have to make that gamma correction. You have to make that relativistic correction. So the lifetimes tend to be, the lifetimes that the true lifetimes or the proper time, these things would be so short-lived that we would never be able to even detect them. They would travel so short distances, they would never be detectable. But for certain particles, we can detect them still. So this problem is a good example of how that is. All right, so let's go ahead and start. So in order to shift to the lab reference frame, we need to know the relativistic velocity of the particle. So this can be calculated by, we're given the kinetic energy is equal to m0c squared. So the mass of the particle, c squared, times gamma minus 1, which is equal to mass times c squared times 1 over the square root 1 minus v squared over c squared minus 1. Oops. Let me just clean this up a little bit, because sometimes it can get a little hard to write on these things. Make this a little bit nicer. All right. Let's make that like this. Okay, so now we just need to solve for v. So this is v squared over c squared. So let's go ahead and keep it in terms of gamma over 1 right now for simplicity. So we get k over gamma minus 1 is equal to m0c squared. And we get, so let's go ahead and now solve for gamma minus 1. Actually, what we really want to solve for is gamma. So we get k over m0c squared is equal to gamma minus 1. And k over m0c squared plus 1 is equal to gamma. All right, so now let's plug in gamma. So we've got 1 over the square root of 1 minus v squared over c squared is equal to, so I'm going to simplify this a little bit. So we get k over m0c squared. Now this plus 1 right here, I'm gonna carry that in. So plus m0c squared over m0c squared, which is equal to k plus m0c squared divided by m0c squared. All right. Now you take the inverse. So let's go ahead and come over here. We got the square root of 1 minus v squared over c squared is equal to m0c squared over k plus m0c squared. Square both sides. Get 1 minus b squared over c squared is equal to m0 squared c to the 4th over k plus m0c squared squared, which is equal to, okay, sorry, not equal to. So now we want to isolate for v squared over c squared. So add that, subtract that, you get v squared over c squared is equal to 1 minus m0 squared c to the fourth over m0 squared plus k squared. All right, now go ahead and solve for, let's go and carry the c squared over. We've got v squared is equal to c squared minus m0 so carry the c squared over, m0 c to the sixth, 0 squared c to the sixth divided by m0 c squared plus k squared. Let's clean this up a little bit. M0 c squared plus k squared. It's supposed to be 2. There we go. So now we can pull out an m0 c squared. So I'm running out of room, so I'll keep it down here. It's equal to c squared minus m0 squared c to the sixth divided by m0 squared. So this is a squared term. So when we pull this out of the squared, we square it. So m0 squared c to the fourth times 1 plus k over m0 c squared squared. All right, so now these cancel. That cancels with the 6, becomes a squared. So now we have, I'm going to create a new sheet here. So now we have v squared is equal to c squared minus c squared over 1 plus k over m0 c squared squared. All right, I'm going to pull the c squared out. Get v squared is equal to c squared times 1 minus 1 plus k over m0 c squared to the minus 2. Okay, so now v is equal to the square root of, so we take the square root of both sides, so that c squared just becomes c. So c times the square root of 1 minus 1 plus k over m0 c squared to the minus 2. All right, so now we have, we know all of this information. We know that the particle at the tau lepton is created with the kinetic energy of 950 mega electron volts. We want to know how long its track would be, like how long does it travel on average, if it, or how long does it travel measured on the lab on average, ignoring any collisions. So we can plug these numbers in. So we can say v, I'm going to use this space over here. V is equal to c. We're going to keep c here because when we talk about relativistic velocities, we always talk about it in terms of a fraction of the speed of light. So we're going to leave c out there. We're going to put your square root 1 minus 1 plus 950 MeV, which is the kinetic energy that it's formed with, divided by the rest mass energy, which is 1777 MeV to the minus 2. And this comes out to, it's going to be created with a velocity of 0.7585 c. So about 75% the speed of light. Or we can say the ratio, or v over c is equal to 0.7585. So that's its velocity. relative to the speed of light. So now the amount of time, delta t, so in order to figure out how long it goes, how far it travels, we need to know how long in the lab reference frame it exists for. So what its lifetime in the lab reference frame is. So delta t, we'll call it delta t lab, is equal to gamma delta t 0. So again, this gamma factor times the its lifetime in its actual in its true time. So this is known. This is basically, it's called time dilation. So now this is going to be equal to 2.91 times 10 to the minus 13 seconds, which you get from the table, divided by square root of 1 minus, so that's this gamma term here, and in the gamma term, it's just the 1 minus v squared over c squared, which is just going to be the 0.7585, which is going to work out to be, sorry, I'm just double checking something here in my notes. Yep, okay. Squared. So sorry, I forgot. This is v squared over c squared. So this is v over c. So v over c squared. That's going to work out to 4. Let me double check the numbers. Sorry, 4.65, 4.465, 10 to the minus 13 seconds. So basically a factor of 2. It lives twice as long at that particular velocity, due to, which is we've determined from the kinetic energy that was measured by it. So this time, now to figure out how far it travels, we have delta x in the lab. It's velocity times time measured in the lab, which is going to be equal to 0.7585 times the speed of light, 3.00, times 10 to the 8th meters per second, times 4.465 times 10 to the minus 13 seconds, which is going to be equal to 1.02 times 10 to the minus 4 meters. It travels for a good 100 micrometers or so, 100 microns, which is definitely a measurable distance. Now, this actually would probably be a measurable distance even in terms of the its true time. But now a more extreme explanation, or a more extreme example of this would be a muon. So a muon is basically a very highly energetic particle which decays into an electron. It has a mean true lifetime, its true time of about 2 microseconds or so, and it's created from cosmic particles. Now, they're basically, it's a cosmic ray. When it enters our atmosphere, if it decayed, it would only make it probably about halfway down or so, based off of its lifetime and its velocity, given its energy. Now, we can measure muons at sea level. So because of how much energy it takes and how fast it is going and how close to the speed of light it is traveling, this value is even larger. So this gamma value is even larger. So it lives much longer. So this gamma value would be larger, because this value would be smaller, because this part would be larger. It lives it lives long enough, basically, to be measured at sea level because of relativistic effects. What it sees and what we see are two different things, based off of relativity. So I just always found that to be a really cool observation. So if you're interested, look up muons and muon spectroscopy. It's a pretty cool thing.